Welcome to a session on Boyle temperature. In this session, we will be dealing with limitations of van der Waals gas equation, some of the problems regarding van der Waals equation, and then we will go for the derivation of Boyle temperature. So, first we will go for the assignment which I have given in the previous class. The assignment is using ideal gas equation and van der Waals equation, calculate the pressure exerted by 44 gram of carbon dioxide when it occupies a volume of 0.537 liters at 373 Kelvin. Given that A, that is the van der Waals constant A is equal to 3.6 atmosphere liter square mole raised to minus 2 and B is equal to 0.0427 liters per mole inverse. The value of R, since these are in liter atmospheres, they have given the value of R in liter atmospheres, that is 0.0821 liter atmosphere per Kelvin per mole. So, this is the data given and we are supposed to find out the pressure exerted by the gas according to the ideal gas equation as well as with the van der Waals equation. So, we will move on to the first one, that is with the ideal gas equation. According to ideal gas, PV is equal to nRT, where P is the pressure, V is the volume, N is number of moles, R is universal gas constant, and T is the temperature, T is the temperature. Okay. Now, rearranging, I am taking V to the denominator, we get P is equal to nRT by V, and this is the expression for pressure according to ideal gas equation. Now, the datas are written here, that is R is equal to 0.0821 liter atmospheres Kelvin per mole, temperature is equal to 373 Kelvin and volume equals 0.537 liters. But here we do not have the value of N, number of moles we do not know, but they have given the mass of carbon dioxide 44 gram, that is mass of carbon dioxide is equal to 44 grams, that is given, but we do not have number of moles. And we know that mass, if you know the mass and molecular mass of carbon dioxide is also is equal to 44 and therefore, mass by molecular mass, so much gram per mole. Okay. So, mass divided by molecular mass will give you the number of moles. So, mass we know, that is 44 divided by 44, that makes the value of N equals what? So, we have got all the required terms, that is P is equal to nRT by V, N is equal to 1 into R 0.0821 liter atmospheres per Kelvin per mole, N is equal to again that is mole, multiplied by 373 Kelvin whole divided by volume, that is 0.537 liters. Liter and liter get cancelled. This is mole and mole inverse get cancelled. Okay. Then again Kelvin inverse and Kelvin get cancelled. So, the final answer will be in atmospheres and calculating we will get it as 57.0266 atmospheres. So, this is the value, that is the pressure exerted by carbon dioxide according to the ideal gas equation, if carbon dioxide molecules are behaving ideally. Now, let us check what happens to the pressure value when we take the van der Waals equation. Van der Waals equation for n moles is equal to P plus An square by V square into V minus Nb is equal to nRT. Okay. Now, I am going to take V minus Nb to the other side. So, I will have P plus An square by V square is equal to nRT divided by V minus Nb. Now, again this is not an equation for pressure. I would have to take this term to the other side. Now, what happens is, since this is added over here, when we take to the other side, it becomes subtraction. P equals nRT by V minus Nb minus of An square by V square, the term coming over the other side. So, this is the expression for pressure according to Van der Waals equation. Now, we are going to substitute the values. P is equal to N is equal to 1, which we have calculated just for the ideal gas equation. So, I will put it as 1 into R is equal to 0.0821. I am not putting the units. Temperature is 373, and finally, you will be getting it in pressure atmospheres, whole divided by what is V? V is 0.537 minus 1 into B. The value of B is 0.0427. This is the first term, minus what is A? 3.16 into N square, that is 1 square, divided by V square, that is 0.537 whole square. We have to be very careful. First, we will solve for the first part. The answer will be 61.9529. Solve for the second part, that will be 12.4840. Of course, the unit will be in pressures. You can take the units and then cancelling, finally, you will be getting it as atmospheres. So, minusing these two, the final answer will be 49.4689 atmosphere. Just check the pressure. See, this is 57.0266, which is a higher value, and when we take in the case of Van der Waals, it is 49.4689. That means the measured pressure is always less, right. So, we have to make a correction. That is why we are having a higher value for this one and a lower value for this one. Okay. Now, let us move on to today's topic. First, we will be seeing Van der Waals equation in virial form, and then we will be deriving an expression for Boyle temperature. That is how, taking the virial equation only, you can go for the Boyle's temperature derivation. So, let us derive the Van der Waals equation in the virial form. Okay. We know that Van der Waals equation P plus A by V square into V minus B is equal to RT, that is for 1 mole of a gas, just for 1 mole. Okay. Now, what I am going to do is, keeping P plus A by V square on one side, taking V minus B to the other side. Since this is the relation between these two is multiplication, when I take it to the other side, it becomes the divided by, or it goes to the denominator. Okay. Next, I am going to keep P here and I am going to take A by V square to the other side. Here it is addition, and therefore, when it goes to the other side, that becomes subtraction. V minus B minus A by V square. Okay. Next, what I am going to do is, see, in this term we have got a V, but in this term we do not have a V. So, I can multiply it with V in the numerator and V in the denominator. So, the equation will be RT by V minus B into V divided by V. Just I have to take out V as a common factor just for that sake. It makes no difference. Okay. Now, what I am going to do is I am going to take V, that is in the denominator, as a common factor. So, that becomes RT over here. I have taken 1 by V outside, that is V in the denominator. So, here taking V makes it 1 minus I have taken this V. So, I will have an expression B by V, okay, minus A by 1 V is taken out. So, it becomes minus A by V. Now, this V is taken to the left hand side, it becomes PV equals RT divided by 1 minus B by V minus A by V. Okay. Now, I am going to take this denominator, that is 1 minus B by V, to the numerator. That is, if I take 1 by x to the numerator, it becomes x raised to minus 1, right. Just like that, the whole term I am going to take it to the numerator. So, this will be RT into 1 minus B by V whole raised to minus 1 minus A by V. Okay. Now, this is of the form, you can check this, this is of the binomial expression 1 minus x raised to minus 1. Here the only difference is x stands for B by V, and in this you will get the expansion as 1 plus x square plus x cube. The whole terms will go on in the positive, because minus and here again to the power minus. So, all the terms will be positive. Now, I can expand this according to the binomial theorem. This is binomial theorem. Binomial theorem. This is a bit of mathematics. So, applying that, I will get PV equals RT into, okay, I will put a bracket, 1 plus B by V, that is that x term. Next will be the square term B square by V square plus B cube by V cube plus etc. It is not over. We have one more term, that is minus A by V. Okay. Now, since this is the only term that is remaining outside, what I am going to take, and this is in divided by V, and here we have one more term divided by V. So, I am going to club it with this, I am going to take this inside. Now, to take inside, here we have a common factor RT, and this term does not have a common factor RT. So, what I have to do is, I will have to multiply RT in the numerator as well as RT in the denominator. Now, the expression will be PV equals RT, okay, 1 plus, you are having B by V, okay, and here also we have got a V. The only thing is we do not have an RT over here, and that RT has been taken. So, this comes out of the, this term comes out of the bracket. So, that can be excluded, and finally, this will be B by V minus A by V RT. So, this will be the term here, plus the rest of the terms as such, B square by V square plus B cube by V cube plus etc. etc. So, the whole thing is within the bracket. Okay. Next, what I am going to do is, I am going to take this RT to the numerator and keeping V as a common denominator. I will make some space over here. Okay. That is PV is equal to RT into bracket 1 plus the first term is B. I am going to take V as a common denominator. Here we will have B minus, I am taking RT to the numerator. So, that becomes A divided by RT, okay, plus B square by V square plus B cube by V cube plus etc. Okay. And this is the virial form of van der Waals equation. So, this is given here, PV is equal to RT 1 plus B minus A by RT divided by V plus B square by V square plus B cube by V cube and so on. This is a virial form of van der Waals equation. So, I have converted van der Waals equation in the virial form. Okay. Next is derivation of Boyle temperature. Now, how do we do that? First, we will have to consider the van der Waals equation for 1 mole of an ideal gas in the virial form. Okay. So, that is PV is equal to RT into 1 plus B minus A by RT by V plus B square by V square plus B cube by V cube and so on. The Camerling-Ons virial equation for 1 mole is PV equals RT into 1 plus B by V plus C by V square plus D by V cube plus E by V to the power 4 and so on. Now, these are known as virial constants. B, C, D all are known as virial constants. B is the second one, C is the third constant, D is the fourth constant and E is the fifth constant and so on. Now, when I compare these two, the virial equation from van der Waals equation and the Camerling-Ons virial equation, I can see that this term, okay, that is the coefficient of 1 by V, here it is B, okay, I am going to equate that is capital B, which is the virial, it is the coefficient of 1 by V, and here 1 by V has got a coefficient, that is B minus A by RT. Okay. So, comparing the coefficients, I can put it as B is equal to B minus A by RT by comparing these two equations. Okay. Now, the second virial constant B is calculated from van der Waals constants A and B of a gas, considering one condition, that is Boyle temperature TB, it is denoted as TB, is the temperature which for B for a gas becomes 0. That is when the second virial constant in the virial equation becomes equal to 0. So, when B is equal to 0, the temperature T will be TB. Okay, so, I am going to modify that at Boyle temperature. That is B is equal to 0. So, 0, okay, first I will write it as B equals B minus A by RT. Okay, here B is equal to 0 and T becomes TB. So, 0 is equal to B minus A by RTB, because B is taken as 0, which means that is the Boyle temperature. Now, taking B to one side and keeping A by RTB on one side, you will have that is equal to B, and TB will be equal to, B will come to the denominator, TB will go to the numerator. So, TB will be equal to A by RB. So, this is the expression for Boyle temperature, which has been derived from van der Waals derivation in terms of virial, similar to virial form, and comparing the virial equation with that, we get TB is equal to A by RB. Okay. Now, the actual TB values for most gases are found to be different from those calculated on the basis of the above equation, which highlights the limitation of van der Waals equation. Again, on calculating the values, it has been found that there is some deviations, which shows that van der Waals equation is not a perfect solution for real gases. Here, they have taken two gases, oxygen and nitrogen, for which we have the calculated and experimental value. Calculated values I have shown in blue color and the experimental values in green color, and just comparing that, you can see that calculated values 521.2, while in the case of experimental one it is only 405.9. In case of nitrogen it is 433 and the experimentally determined is 327.2. So, again van der Waals equation is not a perfect solution for real gases. Now, let us go for the problems. Assuming that oxygen behaves as van der Waals gas, calculate the Boyle temperature given that A is equal to 0.1378 newtons meter raised to 4 mole raised to minus 2, and B is equal to 3.18 into 10 to the power minus 5 meter cube mole raised to minus 1. Now, we are going to consider oxygen to behave as a van der Waals gas. So, the data are entered, A is taken, B is taken, R is given, and our equation is TB is equal to A by RB. Just by heart this, because you may require it for solving problems. Now, substituting the values, 0.1378 newtons meter raised to 4 mole raised to minus 2, okay, whole divided by R 8.314 joules per Kelvin per mole, okay, and B is 3.18 into 10 to the power 5. There is a mistake, it has become 521 and somehow just correct it. Okay. And the unit is meter cube. Okay. So, we have got all these here. Now, newtons per meter square get cancelled, then mole raised to minus 2, mole raised to minus 2 here gets cancelled with this, we will get it as mole raised to minus 1, then meter cube goes here, it becomes newtons per meter and that becomes joules, then newtons meter, and then this is a Kelvin here, so much Kelvin per mole, that will be the unit. Solving that, we will get 521.2092 Kelvin. Okay. Now, taking the second problem, assuming that nitrogen behaves as van der Waals equation, van der Waals gas, calculate its Boyle temperature given that A is equal to 1.39 atmosphere liter square mole raised to minus 2 and B is equal to 0.0391 liters per mole. Now, here we have a problem. Here what the values are given here is all in liter atmospheres. So, we will have to take the value of R in liter atmospheres, that is 0.0821. 0.0821 liter atmospheres per Kelvin per mole. Okay. Now, in this case, that is the point to be noted, and that is why I have given both in the liter atmospheres as well as in the newtons per meter. Here the values are given here A, B, and the value of R taken in liter atmospheres, because here it is all in liter atmosphere per mole, liters and atmospheres. Now, substituting, the value of A is equal to 1.39 atmosphere liter square mole raised to minus 2 divided by 0.0821 liter atmosphere per Kelvin per mole multiplied by B, that is 0.0391 liters per mole. So, mole raised to minus 1, mole raised to minus 1, mole get cancelled. Here Kelvin will be there, liters, and this liter square get cancelled. Atmosphere and atmosphere get cancelled. K raised to minus 1 goes to the numerator, it becomes K. So, the unit will be in Kelvin. The answer is 433.0070 Kelvin. So, this is, you will have to be careful in choosing the value of R. In some cases, they will be giving the value of R. If they are not giving, you should be very cautious in choosing the value of R. Now, I am giving 2 assignments for the next class, that is, assuming methane behaves as van der Waals gas, calculate its Boyle temperature given that A is equal to 0.2283 newtons meter raised to 4 mole raised to minus 2 and the value of B equals 4.28 10 to the power minus 5 meter cube mole inverse. See, this is in SI units. You will have to take the value of R in SI units. The next one I have given, assuming carbon dioxide behaves as a van der Waals gas, calculate the Boyle temperature given that A is equal to 3.59 atmosphere liter square mole raised to minus 2 and B equals 0.0427 liter per mole. Here again you will have to take the value of R in liter atmospheres per degree per mole. Okay. To conclude, let us see van der Waals equation in virial form for 1 mole of a gas, which we have derived taking the van der Waals expression, rearranging it, expanding one of the terms, that is, this is the important point to be remembered, 1 minus B by V whole raised to minus 1. This is what we get on expanding and making some rearrangements. This term is expanded according to binomial theorem, and which that including, that is, A by V inside the bracket by multiplying by RT on numerator and denominator, and finally we get the expression PV is equal to RT into 1 plus B minus A by RT by V plus B square by V square plus B cube by V cube and so on. This is for one virial form of van der Waals equation for 1 mole of a gas. Now, we are going to compare this equation with the Kamerlingh-Onnes virial equation for 1 mole of a gas. See, here you can see that it is 1 plus and we have a term in V, then terms in V square, V cube and V to the power 4. Now, we are not going to take all the terms, we are concerned with only the second one, where we have, see, this is 1 by V and rest is B minus A by RT. Okay. So, the coefficient, this is B into 1 by V. So, I am going to take the coefficients of 1 by V, or I can say that it is a second virial coefficient in the equation. I am going to compare that from van der Waals virial equation and Kamerlingh-Onnes virial equation. Equating that, we get B is equal to B minus A by RT. Okay. Now, I am going to apply the condition, that is at Boyle temperature. Boyle temperature is a temperature at which the virial coefficient B becomes 0. Now, if I am going to apply that condition, when B is equal to 0 means the temperature will be the Boyle temperature TB. Now, deriving an expression, you go to rearrange, you will get it as TB equals A by RB, and this is the expression for Boyle temperature, and this is a temperature at which the gases obey Boyle's law for a certain range of pressure. Okay. Now, it has been found that the calculated values and the experimental values from this van der Waals equation, we have found the value for TB, that is a Boyle temperature. The calculated values are usually higher than the experimental values, or you can say that it is not in that agreement, which shows that van der Waals equation of state is not a perfect solution to apply it to real gases. There are deviations from van der Waals gas equation too. And I have given problems, 2 problems as an assignment. And with this, we conclude this session. Thank you.